In reliability theory and reliability engineering, the term availability has the following meanings: the degree to which a system, subsystem or equipment is in a specified operable and committable state at the start of a mission, when the mission is called for at an unknown, that is a random, time. Simply put, availability is the proportion of time a system is in a functioning condition. This is often described as a mission-capable rate. Mathematically, this is expressed as 1 minus unavailability. The ratio of the total time a functional unit is capable of being used during a given interval to the length of the interval. For example, a unit that is capable of being used 100 hours per week would have an availability of 100/168. However, typical availability values are specified in decimal. In high availability applications, a metric known as nines, corresponding to the number of nines following the decimal point, is used. In this system, 5 nines equals 0.99999 availability. Introduction: availability of a system is typically measured as a factor of its reliability. As reliability increases, so does availability. Availability of a system may also be increased by the strategy on focusing on increasing testability and maintainability and not on reliability. Improving maintainability is generally easier than reliability. Maintainability estimates are also generally more accurate. However, because the uncertainties in the reliability estimates are in most cases very large, it is likely to dominate the availability problem, even while maintainability levels are very high. When reliability is not under control, more complicated issues may arise, like manpower shortage, spare part availability, logistic delays, lack of repair facilities, extensive retrofit and complex configuration management costs and others. The problem of unreliability may be increased also due to the domino effect of maintenance-induced failures after repairs. Only focusing on maintainability is therefore not enough. If failures are prevented, none of the others are of any importance, and therefore reliability is generally regarded as the most important part of availability. Reliability needs to be evaluated and improved related to both availability and the cost of ownership. Often a trade-off is needed between the two. There might be a maximum ratio between availability and cost of ownership. Testability of a system should also be addressed in the availability plan, as this is the link between reliability and maintainability. The maintenance strategy can influence the reliability of a system, although it can never bring it above the inherent reliability. So, maintainability and maintenance strategies influences the availability of a system. In theory, this can be almost unlimited if one would be able to always repair any fault in an infinitely short time. This is in practice impossible. Repairability is always limited due to testability, manpower and logistic considerations. An availability plan should clearly provide a strategy for availability control. Whether only availability or also cost of ownership is more important depends on the use of the system. For example, a system that is a critical link in a production system, for example a big oil platform is normally allowed to have a very high cost of ownership if this translates to even a minor increase in availability, as the unavailability of the platform results in a massive loss of revenue which can easily exceed the high cost of ownership. A proper reliability plan should always address our AMT analysis in its total context. Our AMT stands in this case for reliability, availability, maintainability, maintenance and testability in context to the customer needs. Representation: the most simple representation for availability is as a ratio of the expected value of the uptime of a system to the aggregate of the expected values of up and down time, or if we define the status function as therefore, the availability A, T, at time t greater than 0 is represented by average availability must be defined on an interval of the real line. If we consider an arbitrary constant, then average availability is represented as limiting availability is represented by limiting average availability is also defined on an interval as availability, the probability that an item will be in an operable and committable state at the start of a mission when the mission is called for at a random time. Availability is generally defined as uptime divided by downtime. Definitions within systems engineering. Availability, inherent, the probability that an item will operate satisfactorily at a given point in time when used under stated conditions in an ideal support environment. It excludes logistics time, waiting or administrative downtime, and preventive maintenance downtime. It includes corrective maintenance downtime. Inherent availability is generally derived from analysis of an engineering design and is calculated as the mean time to failure divided by the mean time to failure plus the mean time to repair. It is based on quantities under control of the designer. Availability, achieved, the probability that an item will operate satisfactorily at a given point in time when used under stated conditions in an ideal support environment. It excludes logistics time and waiting or administrative downtime. It includes active preventive and corrective maintenance downtime. Availability, operational, the probability that an item will operate satisfactorily at a given point in time when used in an actual or realistic operating and support environment. It includes logistics time, ready time, and waiting or administrative downtime, and both preventive and corrective maintenance downtime. This value is equal to the mean time between failure divided by the mean time between failure plus the mean downtime. This measure extends the definition of availability to elements controlled by the logisticians and mission planners such as quantity and proximity of spares, tools and manpower to the hardware item. Refer to systems engineering for more details. Example, if we are using equipment which has a mean time to failure of 81.5 years and mean time to repair of 1 hour, MTTF in hours equals 81.5 times 365 times 24 equals 713,940, inherent availability equals MTTF plus MTTR, equals 713,940. 713,940 firsts equals 99.999859%, inherent unavailability equals 0.000141%, outage due to equipment in hours per year, U equals 0.01235 hours per year. Literature. Availability is well established in the literature of stochastic modeling and optimal maintenance. Barlow and Prishan, 1975, define availability of a repairable system as the probability that the system is operating at a specified time t. Blanchard, 1998, gives a qualitative definition of availability as a measure of the degree of a system which is in the operable and committable state at the start of mission when the mission is called for at an unknown random point in time. This definition comes from the MILS TD 721. Lai, Wang, and Tilghman, 1977, developed a complete survey along with a systematic classification of availability. Availability measures are classified by either the time interval of interest or the mechanisms for the system downtime. If the time interval of interest is the primary concern, we consider instantaneous, limiting, average, and limiting average availability. The aforementioned definitions are developed in Barlow and Prishan, 1975, Lai, Wang, and Tilghman, 1977, and Nackles, 1998. The second primary classification for availability is contingent on the various mechanisms for downtime such as the inherent availability, achieved availability, and operational availability. Me, 1998, gives some comparison results of availability considering inherent availability. Availability considered in maintenance modeling can be found in Barlow and Prishan, 1975, for replacement models, Forsey and Hawkes, 1991, for an out-of-N system with spares and repairs, Forsey and Hawkes, 1990, for a series system with replacement and repair, IA, 1992, for imperfect repair models, Murdoch, 1995, for age replacement preventive maintenance models, Nackles, 1998, 1989, for preventive maintenance models, and Wang and Pham, 1996, for imperfect maintenance models. Applications. Availability is used extensively in power plant engineering. For example, the North American Electric Reliability Corporation implemented the Generating Availability Data System in 1982. See also, reliability engineering, safety engineering, reliability. Availability and serviceability, list of system quality attributes, spurious trip level, condition-based maintenance, fault reporting, high availability, references. This article incorporates a public domain material from the General Services Administration document Federal Standard 1037C. External links, Reliability and Availability Basics, System Reliability and Availability, Availability and the different ways to calculate it.